And then that films, and you can zoom by pushing the bottom
What do I show you?
or the top.
Yourself or the screen?
If I'm talking, you can point it at me, and then if I'm showing the screen, you can point it at the screen. And this thing moves this way. Okay? You're like a little camera person. Alright, this is kind of an interesting day. I know it's 2 classes left till you're gone. But today we're going to talk about Einstein's theory of relativity.
I love that guy.
And to me, this was the neatest thing I ever learned. I remember when I first learned about it, how blown away I was. And it's hard to follow. But if you can't follow it, I think you too will be blown away. It gives you some insight into how smart a person Einstein was. And probably right now you're like, okay, yeah, I've heard of Einstein. He's a pretty smart dude. But there's no way to understand how intelligent he was unless you can understand what he figured out. And a little bit of it I'm going to teach you today. So see if you can follow this. All it requires of you is to pay attention. Now, normal motion as we have learned about it thus far, as you've learned in all your classes, the normal, there's Einstein. The normal laws of motion, if I throw a ball, you could clock it with a radar gun, right? Like they do when you're pitching. And you can measure the speed of it. Ellie, you don't want to pay attention to this stuff? I don't think so. So I throw a ball, and you can measure the speed of the ball. Let's say I throw 50 miles per hour. Yeah, I don't have that good an arm, but I can hit the golf ball on it. So if I throw a ball 50 miles an hour, you clock the speed of the ball as 50 miles an hour. What if I'm riding in a car, and I throw it out the window at 50 miles an hour?
Oh, it's going even faster.
If you're standing on the side of the road and you're clocking the speed of that, how fast do you clock it? That ball coming at you?
R plus 50.
50 plus however fast.
Car's going 50 and you're throwing it 50. How fast is it going? 100. That make sense? You're leaning out the car window and you throw the ball at 50. The car's going 50 also.
It's going 100.
So the ball's going to be going 100.
Over 100.
Because your car's going 50 and you throw it forward another 50.
I see you already have the 50 then.
You already have the 50. The platform you're on is moving 50. Are y'all with me?
Yes, sir.
This is great stuff. There was an experiment done by a couple of men named Michelson and Morley. They did it back in the early 1900s, like 1901. And the Michelson-Morley experiment showed that if you shoot a light beam, they came up with a way to measure the speed of light. If you shoot a light beam, it moves at the speed of light, which is how fast? Anyone know the speed of light?
3 point something to the...
250,000 miles per hour. Or miles per second.
Let's do it in miles per hour. Miles per second. 180,000 miles per second.
That's what I was saying.
That's the speed of light. And they showed that you can measure the speed of light, and if you shoot a gun, the light will be going 180,000 miles per second. But then they showed that if you're shooting the light from a platform, a moving platform, let's say the platform's going 1,000 miles an hour, you would expect the light beam to be going 181,000 miles. Or if the platform was going 1,000 miles per second, you would expect the light beam to be going 181,000 miles per second, but it doesn't. Their experiment showed that no matter how fast the platform is moving, light always goes at 180,000 miles per second. It can go no faster. It can also go no slower.
Actually, how about if you're in a medium? Can it go slower?
Well, in a medium, yes, but let's assume it's not going through anything. Well, when Einstein, who was just a young man at the time, when he saw the results of that experiment, it freaked him out a little bit. He said, how could that be? That doesn't make any sense. And what he ended up figuring up from that, he did a lot of thinking about it and did these little, what he called thought experiments. He figured out that what we now today call the theory of relativity. And here's what he figured out. He figured out that light, since it's traveling so fast, it's hard to see the effects of relativity. But what I've set up here to try and explain what he figured out is a little cart or a spaceship that, let's pretend the spaceship can go real fast. And let's forget the cart, let's use the spaceship. And these are people. Do you want to use a male or a female?
Both. Both.
Let's use the guy. Go with the male.
We use the female. No one said that. I'm trying to be different. I'm trying to be difficult. What Einstein figured out was that time changes. The faster you move, time is different for everyone. For instance, I'm moving right now, so my watch is actually ticking a little bit slower than your watch because you're still. Einstein figured this out from this experiment. And he said the faster the object moves, the slower time moves for the person who's moving. And that time is not something that's constant. Time can change depending on the speed that you're moving. And he figured it out from these results. And let me show you why. It didn't make sense to him that light, if an object is moving, light should be going faster if it's shot from the moving object, just like the baseball. But it's not. That was proven by the Michelson-Morley experiment. And so Einstein said, how could it be possible that light is not moving faster when it's shot from a moving object?
The Doppler effect.
It's not that. And here's how it works. Einstein said, time should not be measured as we normally measure it. Time is not the difference between one point and the next point as we're timing something on our watches. What time is measured by has to do with space as well as speed. Let's define time, Einstein said, as the amount of time it takes light to move 180,000 miles in 1 second. A second is the time it takes for light to get 180,000 miles ahead of you. That's what a second is in Einstein's universe. The time it takes light to get 180,000 miles ahead of you is 1 second. Let's use that definition for both these individuals. A spacecraft going at near the speed of light, let's say the spacecraft is going 0.9 times the speed of light. That's really fast. The spacecraft can't go that fast, but let's pretend. Here comes the spacecraft, and right now it fires a light beam out from it. And here's an observer standing on the side watching the spacecraft go by. And the observer starts her watch right when the spacecraft goes by, and the spaceship shoots a beam of light right when it passes the observer. Are y'all with me so far? Here we go, and now the spaceship shoots the beam of light. This meter stick, let me move it back a little bit. This meter stick is going to represent 1 meter is 180,000 miles. 1 meter equals 180,000 miles. Are y'all with me here? Here we go. Here comes the spaceship. It reaches she is? McLean, you can't understand this unless you look. Carson, you're going to be totally off here. Let them settle in. Here we go. We pass our point, we shoot the beam of light. The beam of light is traveling, and it's moving away, but it's being kind of chased by the spacecraft. And it's getting further and further away, and here's 1 meter. 1 meter ends here, 1 meter. And so if she is keeping time, if she has a stopwatch, and here comes the spacecraft, bam, and it shoots its beam, and now the light is 1 meter away from her, 1 second has gone by for her. For the spacecraft, the light, because the spacecraft is moving very quickly, the light hasn't gone a whole meter. It's only gone 20 centimeters according to my model here. So a second has not gone by for the people on the spacecraft. Much less than a second has gone by. And so, if we continue this, we keep chasing this, finally, somewhere out here, the light will be 1 meter away from the spacecraft. That's about right. Now, a second has gone by for this guy, because light is 1 meter away for him. How much time has gone by for her? 1, 2, 3, maybe 4 seconds. 3.5 seconds. So Einstein was saying that time is different for a moving observer and for a stationary observer. Time is different. Time is not static, it's relative. Time changes relative to your motion. If you're moving very fast, time will move very slow for you. And so the person in the spacecraft will actually spin to this person only maybe 1/3 of a second has gone by. For this person, or actually for this person now, the way the model is 1 second has gone by, and for this person 3 seconds has gone by. Imagine if you continued and fast forward that into the future. If you traveled in a spaceship at near the speed of light, and time moves slower for you, you could fly around in a spaceship for what a person on Earth perceives to be 50 years, but when you get back, since you've been going so fast,
Time travel.
only a year has passed maybe. This is a way to do real time travel. If you could travel near the speed of light, you could go into the future.
You won't be able to go back.
You won't be able to go back, but you could go into the future. And you could come back to the Earth at a time you're only a year older. All your buddies are 50 years older.
Wait, does it actually work like that, like on your body?
Actually works like that.
How is that even
Wait a
possible?
second.
This is
So
not
you actually go into
possible.
This has actually been measured experimentally.
I can't.
GPS.
I can't.
If I take a watch, an atomic clock, atomic clocks go many, many decimal points
Many moves.
of a second. And if I take 2 atomic clocks that are keeping exactly the same time, and I put them, one on a plane that travels at 700 miles an hour and flies people around, and I put one on the ground,
Normal plane flies?
yeah, that atomic clock will note a difference. When you get back and you compare the 2 clocks, the one that was on the plane will be slower than the one that was on the ground. A stewardess lives a little bit longer than us
What about astronauts?
because of the relativistic effects. Now, astronauts be the same way with them. However, the effects are only seen when you get close to the speed of light. The effects are only seen well. They're only
Then why don't we
noticed.
just put people in things to make them go to speed of light so they keep it?
Because we don't have anything that can go that fast. It's hard to make.
Can you explain how someone can be a year older and then other people can be a year older?
The fact that you put one year on a different plane. It's fine.
Okay, do you understand this part?
Yes. This person's only been 1 year.
Okay, so for this guy, how much time has gone by?
Is it just like,
And for this person, how much time has gone by?
3.5 seconds?
Okay, so let's just fast forward that. Let's say this guy kept flying at this speed for 1 year. How much time would have gone by for her? 3.5 years. Do you see?
Yes.
If this guy flew for 30 years, for 10 years, 35 years would have gone by for her.
But would it have the same effect, like on your body?
Yes.
Physically?
Yes, time changes. Physically, everything. To the guy in the spacecraft, he doesn't know time is moving slower for him. He's looking at his watch and everything's going the same way it's always has.
What about food? What about
So
your body?
You only need 10 years.
He feels fine.
Everything.
He doesn't notice
that
anything
happens in
different.
time is the
He doesn't
same.
get 50 years
So
older.
can I know a lot?
No, he gets 10 years older. She gets 35 years older.
I don't understand how his body doesn't just like degrade at the same speed.
No, I don't.
What's
I
that?
don't know how his body doesn't like just like
So he
degrade at the
is
same
in real
speed
time for 1
or
year.
like age at the same speed.
Yeah.
Because time is different. Time actually is different for me and you. If I'm moving, it moves a little slower for me.
My life is
And you
right now.
will age faster than I will. Time changes relative to the speed that something is moving. That's the theory of relativity. And it's been proven. It really happens.
We're gonna have to go right now for this one. Get back. I'm still not.
So a pilot actually does live longer
Unless he's flying in the reverse direction of the Earth.
Milliseconds. Because at such slow speeds, when you're going 700 miles an hour in a plane, 700 miles an hour is about 10 miles. Oh no, I'm sorry. About 0.1 miles per second. It's about 0.2 miles a second. That's how fast 700 miles per hour is. It's nothing compared to the speed of light. Barely noticeable. But if you could get a spacecraft that could go almost the speed of light, say 179,000 miles per second,
Could you like literally go to the future?
Yes.
then you would be trailing right behind this light beam. You would release the light beam, and it would stay right in front of you and only gradually get away from you. And if you could go that fast,
You added one more zero.
thank you. If you could go that fast, then when 1 second goes by for you, for a person standing still on the earth, could be months have gone by. Could be years. The closer you can get to the speed of light, the slower time moves for the person that's going that
Well, then
fast.
how does that work as time travel if the time is slow?
Because you're not aging very fast compared to your buddy on the earth.
What if you went like
If you stack up the decimal points against the speed of light, if you're moving 0.99999 times the speed of light, just barely slower, you could actually live millions of. You could. 1 year for you might be 1,000,000 years for someone on Earth, and you could do a big loop around the galaxy, and you come back, and 1,000,000 years has passed on Earth, and 1 year has passed to you. And you only feel like a year has passed. You've been sitting in your spaceship for a year. You went to bed and woke up 365 times, and finally you put the brakes on your spaceship and you come back to the Earth, and 1,000,000 years has passed on the Earth. And you find out that everyone blew themselves up about 500,000 years ago, and you're all alone. Or you find this incredibly technological society that can cure all sicknesses, and it's good that you took off for a year because you had cancer, and now they've discovered the cure for cancer.
This is really wow.
It's really true. It could happen if we could build something that could go that fast, which we can't yet.
When you return to the Earth, are you gonna age like normally again?
Yeah, if you slow down and you go the same speed, if you and I are moving the same speed, which we are right now, then time is moving the same for us. But you know what? Time's moving a little differently. unfortunately now, I'm aging a little bit slower than you are now because I'm moving.
God, you're gonna die so soon, Cass.
Is this blowing y'all away?
Your mind blowing you away.
I'm trying to wrap my mind.
Here's the cool thing. Einstein thought of this basically on his own. He had some friends he kicked it around with, but he came up with it. He wrote it up in this paper. He didn't have any experimentation to help him, but he did the math for it, and it all worked. And it made sense mathematically. And it explained the Michelson-Morley experiment. It explained why you got the same measurement. The guy on board the ship measures the speed of light at 180,000 miles per second. Because for him, 1 second has gone by, and the light is 180,000 miles ahead of him. For her, 4 seconds have gone by, and the light is 4 times this ahead of her. So that works. It explains the Michelson-Morley experiment. The speed of light is the same whether you're moving or whether you're still. The speed of light never changes. And that's the theory of relativity.
So if the Earth stopped revolving and stopped turning, and we went slower, would that mean that we would die faster?
Well, you feel like you're still living the same amount of time, but to someone who's stationary compared to the movement of the Earth, if you could be stationary in space, time would be moving slower for us on Earth than it is for that stationary person in space.
Right.
So you'd have to be stationary compared. See, we're all the Earth is moving, but we're all moving with it. So time for all of us is the same.
So wouldn't it be faster for the person on Earth than the person in space? Because they're moving?
When you're moving, time moves slower for you.
Okay.
The faster you're moving, the slower time is moving for you.
Okay.
That's why the guy going real fast in the spaceship around only ages a year, compared to the 1,000 years that goes by on the Earth.
Physically only ages
The
a year?
faster you move, the slower time moves. Time and speed are inversely related. What's that?
Physically only ages a year?
Yeah. Time is, you feel the same. You feel a year has passed, but for the other guys who aren't moving as fast, many years have passed.
So you have to be going faster than 88 miles per hour. Like the DeLorean.
So it's not.
But they went back in time, which is impossible, unless you're traveling faster than the speed of light, which isn't possible. Yes.
Oh my
It's not like
God.
instantaneous like they were doing. Time still passes for you.
Time still passes for you. It's not instantaneous.
So you can't go back in time?
Only forward. This method only works for going forward in time.
What would happen if you could go faster?
If you could go faster than the speed of light, then you could go backwards in time.
How does that work?
That's not possible.
But you can't do
It doesn't work. It's just theoretical. It works in the mathematics. But there's no way we can get past the speed of light, because there are 2 other things that happens when you go faster, and Einstein figured these out too. The closer you go to the speed of light, so as you go closer to the speed of light, time moves slower.
Okay, so if you hit the speed of light, time will stop.
Objects, we're getting to that. Objects get more massive. So if you were to weigh this spaceship that's getting near the speed of light, it'd be a lot heavier than if it was still. It'd be a lot heavier. The mass of it is greater. And it's not like it gained metal or something that's making it heavier. Its mass is actually more. Because a lot of the energy that's put into speed ends up being converted to mass through Einstein's equation, E equals mc squared. And the closer you go to the speed of light, a lot of that energy turns to mass, and objects get more massive the closer they go to the speed of light. Einstein figured that out too. Another thing he got is that objects get thinner in the direction of motion. So if you measured how long this craft was from one end to the other, it'd be shorter if it's going near the speed of light. And the closer to the speed of light it gets, the thinner it gets. Now, this doesn't affect the person inside the craft that's moving that fast. They see the ship as normal size. But if you saw it go past, it would be thinner. And the closer you get to the speed of light, the thinner and thinner it gets. And the more massive it gets, the heavier it gets too. And the slower time moves for it. And it's not only that the craft gets smaller. It's everything in the direction of motion gets smaller. So the entire universe in the direction of motion gets smaller, gets thinner, as you go nearer the speed of light. And you can actually get from one place to another faster. Time's moving slower, and space is getting smaller. You could actually, theoretically, if you could go near the speed of light, you could travel around the whole galaxy, the whole universe even, in one human lifetime, if you could get going near the speed of light. Because of this, what we call dilation of space. It's amazing, isn't it? Yeah.
If the people on Earth who are not moving as fast as the person in the spacecraft could somehow see the person in the spacecraft traveling through space, would it appear?
They'd be real slow moving. They'd be a lot thinner if you could see them. And they'd be more massive if you could weigh them.
The spacecraft.
The spacecraft and the person in it.
And the person.
Yeah.
So would they see them traveling for a year or for 50 years?
For 50 years.
Okay.
Because 50 years is passing to this person, the observer. That's right. If you're interested in this stuff, it takes a lot of study to understand it. This is a good book that kind of introduces it. And this is how I was introduced to it. Carl Sagan is an astronomer, which when we come back from the break before Christmas, we'll talk more about his work. He does a lot of this. He was attributed with a lot of the SETI stuff. Do you know what SETI is? The Search for Extraterrestrial Intelligence. He wrote a lot of books. Very, very smart guy. I showed you a video he did on the guy that figured out that the Earth was round. Do you remember that? That was Carl Sagan. Was narrating that. And he explains it real well in here. And he even shows some spacecraft that he's proposed that if you built them, they would go near the speed of light or close to it. See this page? It's even got the designs for the spacecraft. And those are possible with today's technology to build those. And it talks about them all in here and how space and time dilation works. It's kind of a good introduction to it. There's a lot of other stuff in this book. It's a great book. But the point of all, why are we bringing all this up now? It's kind of blows you away that Einstein could think of such a thing, and that's why he's often considered to be the smartest person that ever lived. Question?
We're supposed to leave it to the outcome.
Okay. Now I'm going to call you all out? Okay. See.
Bye.
Here's where they talk about some of the stuff that I was saying. I want you to make sure you do your reading. The reason why they bring this up now is because gravity has an effect on all of this. The more gravity something has, gravity kind of works the same way as speed does. If you think about a spacecraft has to use a bunch of energy to go fast, right? Well, a spacecraft also has to use a bunch of energy to escape the gravity of something. And the laws of physics don't see any difference in between the two. If you're using energy to go fast, or using energy to escape the gravitational pull of something, it's the same effect. So if here's a black hole in space, and you're being pulled toward the black hole, and you're going real fast, using a lot of energy trying to get away, it's just like you're traveling real fast through space. relativistic effects occur here. And time slows down for you as you're being pulled toward the black hole and trying to get away, even if you're not moving. Let's say the black hole is pulling so hard and you're going that way as fast as you can and you're stuck. And you're accelerating that way, but because of the tough gravity, the hard gravitational pull, you're not going anywhere. Could you imagine such a thing? It's kind of like a tug of war. Relativistic effects would take place on you inside your spaceship. And if you're using enough energy, time will slow down for you, just like you were going at near the speed of light. And Einstein figured this out. Einstein said, gravity is just like motion. And he kind of compared it to, have you ever heard, if you're falling in an elevator, and the elevator's falling with you, what would it feel like to you? I mean, obviously, when it hit the ground, you'd feel something. But what would it feel like while you're falling? It would feel like zero gravity. You'd just be floating in the elevator. Imagine an elevator shaft that's real long. You'd just be floating in the middle of that elevator. And you wouldn't feel any movement at all. But you're moving really fast, aren't you? But relative to the elevator, you're moving the same. These kind of thought experiments, if the elevator is moving upward real fast, you'd be pinned to the ground of the elevator, wouldn't you? If the elevator takes off going up real fast, all of a sudden, you're kind of pushed down. So gravity is the same thing. Gravity is like a pull, but it's kind of the same. Gravity is the same as if you're moving real fast in one direction. It's the same sort of thing. And as it turns out, it is the same thing in the laws of physics. Gravity and motion are very closely related to one another. Einstein figured this out too. And he said gravity ought to affect light. He said a black hole will bend light around it. And at the time, nobody thought that gravity could affect light. And they said, how do you know that? How do you know that, Einstein? He said, the equations show it. He said, here's a way to prove it. He said, wait till the next solar eclipse, which was coming up in about a year from then. He said, go out during the solar eclipse. And here's the sun. Here's the sun shining, right? And if you could imagine, if you could remove the sun, just make the sun go away, of course there would be stars in the background, right? The background sky would have stars. And he said, but the sun, Einstein said, the sun has a lot of gravity. And if the sun is there, the position of the star will be shifted a little bit by the sun's gravity pulling on the light waves of the star. And so he said the way to prove if gravity can affect light is in the next solar eclipse. Because in the next solar eclipse, the moon will move over the sun, and you'll be able to see the background stars and where they are. And then when the sun moves away from this position, remember the Earth is going around the sun, so really the Earth would move to a new position, and you could see where the stars would have been. Einstein said you'll notice that the stars would be in a different position if the sun were removed. And so they waited a whole year until the next eclipse. In the eclipse, when you could see the stars that were near the sun, the stars were out of position. Exactly as much as Einstein had predicted they would be. And it was kind of everyone was waiting to see if Einstein was going to be right about this. And the day came around, and he was right. And so he suddenly became this superstar, where there had been no evidence of any of his ideas and predictions until then. That was the first solid evidence that relativity was right. And for this, he is famous. And so there are all these relativistic effects that go on. Einstein figured out what gravity is. You ever wonder what this is? Why this falls down? Why not when I release it? Does it stay there? Gravity is kind of like if you think about a pool table with a rubber surface. See this? They've set up a pool table with a rubber surface, and they've set something heavy on it. You see that brick? It's weighting down the pool table there. If you were to roll a ball at the brick, it might do circles around this thing. Gravity is curved space caused by heavy objects. Any massive object actually curves space. And so the reason why this dice falls to the ground is because the Earth is curving space and causing things to fall into these little curved depressions caused by massive objects. What's the most massive object that we know of? Way more massive than the sun.
The other one, the galaxy.
I'll give you a hint. We just learned about black holes. There's nothing more massive than a black hole. It's of infinite mass. Well, no, it's not of infinite mass, but it's of a lot of mass. It's of infinite density is what I mean. And the more dense and massive an object is, the greater the deflection is, and the greater gravity it has. You could imagine this thing would really be deflected by this black hole as it rolled across it. In a mere 10 or 15 years, Einstein discovered why gravity works. He discovered that time is not relative. That time is relative. That mass is relative. That space is relative. He changed the way you look at the world. And I don't expect you to understand all this right now. But you should try to understand it throughout your life. It makes things a lot more interesting. There's a lot more out there than you realize. I know I've been talking a lot, and it's hard to follow everything. You get bored.
Thanks to the musings of an obscure clerk working in the Swiss patent office, our next great discovery revealed that the universe is a strange, mysterious place. Every century, Mercury's perihelion advanced slightly, a change that Newton's equations could not account for. In a bold and startling move, young Einstein proposed his own theory to explain the puzzle of Mercury's orbit, and in the process, developed a theory that refined Newton's laws of gravity. Michio Kaku is a theoretical physicist at the State University of New York.
Newton says that gravity travels instantaneously throughout space. And that's where Einstein thought there was a weakness in Newton's theory. He wanted a theory that could explain gravity. He wanted a theory that could explain acceleration and zigzag and circular motion. There has to be waves, gravity waves. It takes time for gravity to work its magic.
To propagate.
So if the sun were to disappear, it would take 8 minutes for us to know about that fact. Even gravity travels at the speed of light. Einstein needed a new picture to explain that. And that picture was curved space. That space itself has curved, and that's why objects move.
Einstein believed that his concept of curved space was responsible for shifting Mercury's orbit. Einstein called his idea the theory of general relativity.
Imagine a trampoline net and place a bowling ball in the middle of a trampoline net. The bowling ball sinks into the trampoline net, and now shoot a marble around the trampoline net. The marble will orbit around the bowling ball. Now, from a distance looking down, Newton would say that there is a force, an instantaneous, invisible force pulling the marble down to the bowling ball. But Einstein would say, there's no force, there's no pull, is just a trampoline net. And why is the marble orbiting around the bowling ball? Because the trampoline net is pushing the marble. Therefore, why am I sitting on this chair? Not because gravity pulls you to the ground, it's because space pushes me down toward the planet Earth.
The idea that space itself was warped by mass was too strange for many to accept. An approaching solar eclipse gave scientists the perfect opportunity